Hello. I'm going to do some notes here about collisions. So in a collision, I'm just going to qualify that. This is collisions and also explosions. So anytime that you have two objects that are going to somehow interact with each other, sometimes they stick together, sometimes they were together at the start and they explode away from each other, whatever. But two objects that are interacting with each other is what these have in common. And I'm going to ask you to remember Newton's third law. Newton's third law is that when two objects, that the definition of a force, let me write it down, something like what you have in your notes back from Unit 4, I guess. A force is an interaction between two objects, kind of like in a collision or an explosion. Therefore, the force experienced by object 1 is equal but opposite direction as the force experienced by 2. It's got to be equal and opposite. Why? Because it's the same force. There's only one force. So you can't have a different amount if there's only one interaction. If we wanted to write this in equation form, you could write it something like this. You could say force of on object 1 from 2 is equal but opposite in direction to the force on 2 from 1. And now, since we're talking about impulse and momentum, and we know that this is true, we might look at this equation and say, I've got force on both sides, and since when two objects interact, they interact for the same amount of time. So what if I multiplied both sides of this equation by time? I'm dropping the from 2 from 1 part. So this is the force on 1 is equal opposite. That's totally legit move, right? I'm multiplying this equation by the same thing on both sides. Okay, well, that's the change in momentum of object 1. And this is the change in momentum of object 2. And if I put both of those on the same side, that's kind of a big deal. There's no change in the total momentum. So whatever the change in momentum of one is, the other has to have exactly the opposite change in momentum. And that is what we mean when there's no total change in something. Just like in the last unit, no total change in energy, we say that energy is conserved. So here we say that momentum is conserved. All right. That's pretty cool. Now what can you do with that? Lots. So I'm going to start with this equation that says, I'm just going to recopy the last line that you have on your page, so you can just keep going. Okay, change in momentum of object 1. That's mass 1 times its final velocity minus mass 1 times its initial velocity. I'm just going to make a note. I could put, like, if you're wondering, oh, well, both things are moving, so which velocity is this? We're never going to multiply the mass of something by the velocity of another thing. So if I'm multiplying the mass and velocity, this means this definitely is a velocity of this mass. Otherwise, if we force ourselves to be more specific, the subscripts here are going to get really messy and complicated. You're going to have two things, like that this is final and it's also of 1. So can we just decide right now, right here, that we are not ever going to multiply the mass of one thing times the velocity of another thing? That just doesn't make sense to do that now or at any other time. So that's the change in momentum of 1. And then for object 2, times its final velocity minus object 2 times its initial velocity. And could add those two over to the other side. And I'm actually going to write it with that side first. I'm going to write m1 initial m2 times its initial velocity. Those are not the same thing, right? That's the initial velocity of 1. This is the initial velocity of 2. Equals mass 1 final plus mass 2 final. So all of the masses and velocities here multiplied together before the collision or explosion equal all the masses and velocities multiplied together added up after the collision. So this is our total momentum before the collision, and this is the total momentum after the collision. Yeah. So that's a big deal. I'm going to just add one more little note here. If your kinetic energy before is equal to your kinetic energy after, those are totals. And we call this an elastic collision. If the two objects stick together and like become one object, like classic momentum problem is like firing a bullet into like a wood block or something like that. Those two objects have effectively become like the same object. It's not like a bullet embedded in a block that moves together. If two objects stick together, we call this a perfect inelastic, or sometimes we'll just say inelastic. We'll drop the perfect. An inelastic collision. Hopefully that's fairly intuitive to you. Elastic, bouncy, bouncy. Things bounce off each other. If it's perfect, if no kinetic energy is lost, then we call that an elastic collision. Two objects stick together. then we call that a perfect inelastic collision. They become one object. All right. I'm going to show you, kind of like our LOL diagrams, we're going to make these little diagrams here where we keep track of, again, this is just like an accounting device to help us keep track of what's going on. And I'll show you when I do this worksheet in a minute, and I think probably we'll do an example in class. But this will help us see, like, I've got this much positive and I've got this much negative, so it has to add up to what this total is, and that my total on the other side would have to be the same. So we'll do an example in class, and I'll also show you on this sheet how we're going to do our accounting for momentum.